ARM Microcontroller and Embedded System, Module 5, Session 9. Today we will discuss topics including simulators, emulator, debugger, and different hardware debuggers used, and finally boundary scan method used. So, what is a simulator? We will discuss first. So, a simulator, what basically it is. So, if I'm not wrong, in fifth semester DSP lab, we had many programs on part B. Experiments included convolutions, linear and circular. So in part B, the mode which we had selected, so we were implementing the DSP experiments using the Code Composer Studio, which was IDE there, and there we had two modes, simulator mode and one more was emulator mode. In the simulator mode, we were not bothered about the target itself. You were not being given with the target, and without using the target machine, you were writing the code using a IDE, which means the IDE comes with the simulator too, and literally the experiment output would also be shown in the simulator window itself. So, what do you mean by simulator? Simulator implies it's a kind of a tool, and it comes along with your IDE. Okay, so it is a software tool literally used for simulating. Why would we go for simulation? It is to ensure that if we simulate our basic applications, then we will be confident enough that later we can run the same code in the development platform, and we can get the functionality very quickly. For example, even in sixth semester right now, you've been asked to work on the Proteus tool. So Proteus tool, you can think as if it's a simulator wherein all your embedded C code, which is meant for ARM application, you can run it in the Proteus toolbox also. You do not require a hardware. So that's a kind of a simulator, and once the simulator gives you the correct right result, then you can literally go with the development environment. Then you can use your target machine, and you can give the connection, physical connection, and you can ensure that you'll get the majority of the times, like 90% of the times, if you're getting the simulator result, simulated output you'll be getting, then definitely you will get the output in while developing also. So that's one advantage if you are using simulator. Okay, so literally the IDE will provide simulator support. Literally, Code Composer Studio has a simulator platform to work with. So if you consider one more example for simulator, you can think as if you're familiar with Android Studio. In Android Studio, uh, uh, basically you use this tool to develop application in Android platform, and that tool itself comes with different virtual smartphones in it. And this application which you design using Android Studio could also be run on those virtual machines. Could be Samsung Galaxy is available, and other Samsung mobiles like Samsung A7, even those features are available. So you design your application and try to run it on your soft phone. Literally, you call it as a soft phone, which has a GUI and which has all the features which your physical smartphone is having. So you can try your application to run it first on that virtual soft phone. Later, if it runs properly, then you can put it in your machine, put it in your physical machine. So that's one more example which I just wanted to address here. So hope you're familiar with simulator. So some of the features of simulators are purely software based. You don't require a target, and that's what the second sentence talks about. Doesn't require a real target system, and this is very primitive. Very primitive implies you do not have all facilities in the simulator mode, simulation mode. For example, if you have used Proteus, tool for developing ARM codes, you might have observed that you have for your ARM7 microcontroller LPC2148, which was IC which was used there, alternative to LPC1768. They do have port 0 and port 1, but the number of pins in both of those ports are limited. It's not like all 32 pins are available, so there is a restriction imposed on IO pins. And when you're developing, like a simulator might pose some restrictions, but emulator doesn't have it. And lack of real-time behavior, it is a simulator, which means for running a real-time applications, like probably a speech signal if you want to record or signal, and if you want to process it, probably noise cancellation project could be. So in that case, you cannot try to use this kind of a simulator. You require a proper target with the CPU embedded in it to ensure that it gives you the desired application, right? And limitations of simulator would be it deviates from the real behavior, because sometimes the clock frequency for your simulator chosen would be different, and in your real working environment the clock frequency might also be different. So in that case, definitely the way this executes, it might run very quickly. This may not give you the correct result as well, so delay may have to be changed. You might have observed this scenario if you have used Proteus again. To some extent, if you want to run the same program given in your lab, CLM, same program may not work sometimes. To some extent, you may have to change the delay so that it will give you the correct answer. So if you try a stepper motor program or DC motor program to run it in Proteus platform, then definitely you will come to know what basically deviation from real behavior means. Okay, so delay and all you have to tune a bit. And lack of real timeness, because as addressed, this doesn't support this is not meant for a target. So if you want to process real time signal, then definitely you may have to use a target. So simulation, this is one of the disadvantage for a simulator effects. Now the next happens to be the emulator. So emulator is actually a hardware device. It's a hardware device, and it does what it does is it emulates the functionality of the target device. So for example, in fifth semester lab, let me take back. So we had used a JTAG emulator, which is kind of this kind of a model. So one end of the JTAG emulator was connected to the host machine, was connected using USB port, and one more end was connected to your JTAG connector. So which was there in your board. Okay, that was also a USB slot itself, if I'm not wrong, and it depends. It might if you have a USB support, USB support might be there. Sometimes you might have a serial support also. It could be a USB to serial adapter. Okay, so basically what emulator does is it tries to copy what basically this does. So you give some commands. The commands will go to this target machine using this emulator, and it will process the data accordingly, and later that data what it processes, you can observe it in your host machine. So whatever this does, whatever the target does, target processes, you can visualize the information in your host machine with the help of this emulator. So whatever this does, this copies that, this mimics it, and you can get it in your host interface. For example, let's say that interfacing program, we had used an emulator. We provide the input sequence x of n, and we provide h of n sequence. So those commands reaches the target board, and the target processes it. After processing, all the information you can observe in your desktop machine. That is the result of x and h. If it's a convolution, you get y of n, and that information literally will be monitored in this monitor. In the monitor, you'll get the information. So that is due to this. So what this does, This doesn't has a monitor, but that privilege or that feature could be made available with the help of this debugger. Okay, so if you go wrong, then definitely you can stop the debugging process and you can do modifications wherever required. So thereby you can effectively design your application. Now, coming back to debugger. So we know what debugger is. Debugging, you can have a firmware debugging or you can have a hardware debugging. What is firmware debugging? Firmware debugging is strictly software based. So to debug a firmware, we need to figure out is any bugs. Is there any bugs in the code that we need to figure out? Hardware debugging could be debugged, or it could be rectified using different hardware debugging tools, which we will discuss. So basically, first, what is debugging? Debugging is actually a process of diagnosing. Diagnosing means it is a resolving process. It tries to fix the issues if it's having. Okay, so diagnosing the firmware execution, that's one job. So try to ensure that the firmware what you have, what you embed in your embedded product, works accordingly as per as your requirement. That it will try, and if there is any issues along with, so it will be highlighted and you can fix the issue later on. And also one more thing is firmware execution, monitoring the target processor's register and memory while the firmware is running. So you might have observed when you run a particular application, there are different components present in your debugger. That happens to be the watch window, CPU registers. All these components are available in your debugger. So all those information you can view, and based on its content you can figure out what's happening, and does the application is running as per as your requirement. So all those can be identified using the debugger window. Okay, so that's what this means. So monitoring the target processor's register content you can visualize, memory content also you can visualize. You can go to the memory, whether right now the code is it working in the data segment or whether it is working in the code segment. Even that you can visualize. Okay, and it can be visualized when the firmware is running. So this can also be done at the same time. Okay, and coming back to the hardware debugging, specifically firmware debugging is a process in which we figure out whether there is any bug present in the firmware due to which it behaves unexpectedly. So it creates unexpected behavior. The application desired may not match the required application. So that could be fixed, or sometimes there might be a syntax or probably logical error. So logical error could also be fixed. Okay, and that's about firmware, which is completely software debugging. You call it as a software debugging also. Then you have a hardware debugging. In hardware debugging you have many tools for debugging your hardware, which could be in the form of why would you require, first of all. So first thing, firmware might be bug free. So what is bug free? So this may run properly. The application what you expect, you may get it. Okay, but there are other things which you need to consider. It could be related to the target, that is the embedded product, or the hardware itself may not work properly. They may not work properly due to the following reasons. It could be a dry soldering of the components. You have an embedded product which might have various components or various devices in it, and between the devices, if you might have soldered two devices. So in that case, if it's a dry soldered stuff, then definitely there will not be a connection established between the two devices. So that might be one of the reason which we need to figure out. And also you might have given the PCB for fabrication, and the PCB manufacturers might give you back the device, but certainly they might miss some components which might go unnoticed, and that is also a error which you will certainly notify, and that could also be that is also a hardware debugging issue. So this kind of issues try to identify, and how is that you can identify this kind of issue. So drive soldering, is it a missing component or connection issue, or is it a noise, you know, all those things that needs to be addressed. So all these are issues for hardware debugging, due to which we need to use some debugging tools. So some of the debugging tools which you will be using for addressing all this following issues are, the first one, magnifying glass. You know this is what this is. So literally, magnifying glass will ensure that if there are any miniature component present in your motherboard, it will magnify it, and you can certainly figure out whether there is any connection missing, and you can fix that. So this is actually the traditional method which literally everyone does it, to figure out if there is any you know, connection, if it's connected or not, using the lens or magnifying glass, the first method. Second method is a multimeter. So this tool, this method can also be used. Suppose if you think that if the data is not propagated from one device to another device properly, then you can always go to the input terminal and output terminal of the device, respected devices, and you can check whether do you get current there, or you can even measure the voltage at those points. So by doing so, you can check the, literally what you're trying to do is you're trying to check the connectivity. So if the connectivity does exist, and if it's working according to your requirement, then you can proceed with. So you can choose this tool also for you know, tackling or handling the issues in the hardwares. And the next one is actually your digital CRO. So CRO, crystal oscillator, you can use this oscilloscope, okay, and this could also be used for figuring out whether the signals which you're going to get might be in the form of an analog signal. Literally it will be an analog signal, in because we talk about a circuit there, and this signal, whether it is you know, in the form of whether it is a sinusoidal signal you're getting, square signal you're getting from one device to another device, so even this you can measure. So okay, so digital CRO is one more tool used for addressing the issue which was just pointed out. The next one is a logic analyzer. So logic analyzer, logic implies binary. So sometimes your circuit might provide or give you a binary signals, zeros in the forms of zeros and one, and for analyzing you have a separate tool which you call it as a logic analyzer. This is not meant for handling analog signals. For capturing digital data in the form of zeros and one, we use this logic analyzer. The last one is a functional generator. Functional generator is not a tool used for you know, resolving the above mentioned issues. Rather, it is used for used as a, you know, input device to provide a signal to another device. So you can assume if there are two ICs, one IC is supposed to provide a signal to another IC. Think as if the signal might be in the form of a periodic square wave. So square wave needs to be given to second IC with the help of a first IC. In that case, you can use this function generator to make the communication possible. Okay, so these are actually the various tools used for hardware debugging. Okay, and the last topic is a boundary scan. So why do you prefer this boundary scan? So boundary scan is a concept which literally will be used when you're using integrated circuits. So assume that you have a motherboard, and that motherboard is having many ICs, integrated circuits, and this integrated circuits needs to be communicated with each other. So in that case, boundary scan helps you a lot, because when the size of the IC is very small, miniature in size, then it becomes very difficult for you to figure out if at all there is a connection gone wrong or not, with the help of your hardware debugging tools like the above mentioned one like magnifying glass, even the multimeters, oscilloscope may not play a huge role over here because almost all the components present in your integrated circuits are very small, and it would be very difficult for you to figure out whether there is a make or break in the connections, or make or break in the circuits. So when the circuit size is very small, then it becomes new methodology to be used for figuring out whether there is any issues with respect to the ICs in your motherboard. So for that purpose we use concept of a boundary scan. So boundary scan is a technique used for testing the interconnection among various chips. So just understand various chips, which means integrated circuits. You might have 3 or 4 integrated circuits, and in that case you may use this boundary scan method to identify if there is any connection, break or make. Okay, and every JTAG interface would use this boundary scan method for figuring out the connections. Okay, and the chips which support boundaries can associate a boundary scan cell. So literally how it looks like. So for example, if I consider this as your whole PCB with the 3 devices, and each device, this is one IC, 3 ICs you have, and you have inputs and output line. So for each pin there will be a boundary cell with defined size for each of the pin, and this cell will be different for different ICs. Okay, and you call this as a boundary cell. Okay, so that's what this means. Chips which support boundaries can associated with the boundary scan cell. They do associate a boundary scan cell with each pin of the device. Each pin of the device would have a boundary scan cell. Okay, and main some of the signals which we talk about when it comes to JTAG port happens to be TDI. TDI stands for test data input, test TDO, test data output, test clock, test reset, and test mode select. So these are the 4 signals used in your JTAG, and altogether you call this whole stuff, you call it as a test access port. Okay, TAP would consist of this 5 pins, and each pins are addressed as TDI, TDO, TCK, TRST, and TMS. So every device which supports JTAG should have this tab. Okay, so this tab or test access port should be made available for every devices which supports JTAG, and also the PCB which you are using, above which you lay the devices, should also have JTAG, or this tab feature should also be included in your PCB for making the connection happen. So finally, this is your diagram. The connection between the test data signals we will just talk about. So you have, let's assume that there are 3 ICs, IC1, IC2, and IC3, and each of these ICs are having those 5 important signal, and here mainly 3 signals are taken: TDI, TDO, and TCK. Similarly, this 2 has same information. Now the connection between the PCB and the 3 devices should go in this manner. The TDI of the PCB, because this PCB whole motherboard should also have this 5 signals. So the TDI of the signal should be connected to the TDI of the first device, and the connection between this first device and second device, TDO of the first device should be connected to TDI. Okay, and TD out of the second device will be connected to TDI of the third device, and the TD out of the third device is connected to TD out. So this way you form a chain in the sense, from this you come in, from this to first device, from first device to second device to third device, and third device back to the PCB. Okay, so this forms a chain. And the other signals which should also be considered here, there should be a synchronization that is test clock is common here, and it is given to device 1, device 2 and device 3 as well. Okay, so this is about your boundary scan structure. So you require a software again to ensure that everything is working fine in this complete area, and that software is implemented using Verilog code, and yeah, that's all you have. So suppose if things doesn't work, you get a error when you run that program. Okay, if the boundary scan is not matching, so you'll get an error in the program which is written in HDL script. Okay, so this completes module 5.